Your phone knows the time so precisely that it can help locate you anywhere on Earth. A navigation app can guide you through an unfamiliar city because satellites thousands of miles above the planet are constantly sending carefully timed signals toward the ground. Those signals have to account for the speed of the satellites, the strength of gravity, and the fact that time does not pass at exactly the same rate everywhere. A tiny error would grow quickly, flights would drift from their routes, financial networks would struggle to place transactions in the correct order, communication systems would lose synchronization, power grids would become harder to control. The digital world surrounding you depends on clocks agreeing with one another to fractions of a second that no human being could ever feel. Yet for most of our history, none of this existed. There were no minutes, no seconds, no time zones, and no universal hour shared across distant cities. There was sunrise, darkness, the changing moon, the slow movement of stars, and the recurring arrival of seasons. People knew that the world followed patterns, but those patterns had not yet been divided into the schedules that now organize almost every part of our lives. The journey from that ancient world to yours began with a simple act. Someone looked carefully at the sky. A farmer noticed that certain stars appeared before the river rose. A priest learned that the moon could organize ceremonies. A merchant discovered that shared dates made agreements easier. A monk needed the night to be divided into hours. A sailor needed to know where his ship was after the coastline disappeared. A railway company needed distant towns to stop keeping different times. A physicist needed a clock stable enough to test the laws of the universe. Each of them faced a practical problem. Together, their solutions built the invisible system that now decides when you wake, when you work, when a train leaves, when a market opens, when a message arrives, and when a machine performs the next operation in a sequence too fast for the human mind to follow. How did people learn to measure something they could never touch? Why did calendars appear long before clocks? How did the authority to declare a new month or a new year become a source of political and religious power? Why did cities begin trusting bells and mechanisms more than the position of the sun? How did accurate time help ships cross oceans, railways connect nations, and factories regulate human labor? And how did the search for a perfect clock eventually reveal that time itself changes with motion and gravity? These questions lead to an even larger one. How did the human search for time gradually place calendars, clocks, schedules, deadlines, and synchronized seconds at the center of almost everything we do? Tonight, we will follow that transformation from its earliest beginnings. We will return to a world where the sky was the only clock anyone knew. We will watch farming communities turn celestial cycles into calendars. We will see shadows divide daylight, water measure the night, and mechanical clocks begin imposing a shared rhythm on entire cities. We will follow the pendulum into the scientific revolution, travel across the oceans with John Harrison, and enter the age when railways and telegraphs forced distant communities to agree on the same hour. Then we will move inside the atom, where the most precise clocks ever built changed the definition of a second and helped expose one of nature's deepest secrets. The history of timekeeping reaches far beyond the history of instruments. It follows the gradual construction of a world in which time became visible, countable, tradable, enforceable, and eventually unavoidable. Every appointment in your calendar belongs to that history. Every alarm, every deadline, every departure board, every GPS route, and every moment when you glance at a screen to see whether you are early or late, carries the result of thousands of years of observation, argument, invention, and control. The story begins before anyone had invented the question, "What time is it?" It begins beneath an open sky, where human beings first discovered that survival depended on remembering when the world would change again. Imagine waking in a world where no one knows what time it is. There is no glowing display beside your bed, no watch on your wrist, no calendar on the wall, no reminder waiting on your phone, and no clock tower overlooking the town square. There are no train schedules, no business hours, no countdowns, and no agreed moment when one day officially becomes the next. Instead, there is only the world itself. A pale band of light slowly appears above the eastern horizon. Birds begin their morning calls. Mist drifts across rivers and fields before the warmth of the sun slowly dissolves it. Smoke rises from cooking fires. Families emerge from shelters built from wood, stone, mud, or woven reeds. Children wake. Hunters prepare their tools. Farmers walk toward their fields. No one asks what time it is. The question has not yet entered human language. People ask different questions instead. Has the sun climbed high enough to begin working? Will darkness arrive before we reach the valley beyond the hills? How many nights remain before the moon becomes full again? Will the river flood soon? Those questions mattered because every answer carried consequences. Leaving too late could trap a traveler in darkness. Planting at the wrong moment could threaten an entire harvest. Missing the return of migrating animals might mean weeks without enough food. Long before people learned to measure time, they learned to depend upon it. They simply did not call it time. At first, our ancestors probably experienced the world as a continuous flow of changing light, weather, temperature, and seasons. Gradually, almost imperceptibly, they began recognizing that these changes were not random. Morning always followed night. Winter always gave way to spring. The moon returned to familiar shapes. The stars rose in recognizable patterns. Year after year, the same natural events repeated themselves with astonishing reliability. That realization may have been one of humanity's earliest scientific discoveries. No one invented it during a single, remarkable moment. There was no brilliant observer who suddenly understood everything. The knowledge accumulated across thousands of years as countless people noticed small regularities in the world around them. Parents pointed toward the horizon while teaching children about the seasons. Hunters remembered where certain stars appeared before migrating herds returned. Elders noticed that rivers reached their highest levels after familiar patterns appeared in the night sky. Observation slowly became memory. Memory slowly became shared knowledge. Shared knowledge became tradition. Long before writing preserved information, human communities were already preserving patterns. Those patterns quietly shaped daily life. A hunting group that remembered when animals migrated held an advantage over one that relied only on luck. A community that understood seasonal rainfall could prepare food before difficult months arrived. Fishermen who recognized recurring movements of tides and fish could plan their work more successfully. Knowledge of recurring cycles gradually became a form of survival. Unlike strength or speed, it could be passed from one generation to the next without being lost. Every child inherited not only tools and stories, but also an increasingly detailed understanding of the world's rhythms. This slow accumulation of knowledge transformed humanity's relationship with nature. People were no longer responding only to what they saw in the present. They were beginning to anticipate the future. That ability changed everything. The difference between reacting and anticipating seems almost ordinary today because modern life depends upon it. We check weather forecasts before leaving home. We buy airline tickets months in advance. Farmers use seasonal predictions. Businesses prepare budgets for the coming year. Our distant ancestors possessed none of those tools. Their only forecast was careful observation. And the greatest source of information stood above them every day and every night. The sky became humanity's first library. Every sunrise added another page. Every season repeated another lesson. The sun was especially important because its behavior changed in subtle ways throughout the year. Imagine standing on the same hillside every morning for many years. At first, each sunrise would seem identical. Then, slowly, you would notice that it was not. During one part of the year, the sun appeared farther north along the horizon. Months later, it rose farther south before gradually returning once again. The point where daylight first touched the earth drifted almost imperceptibly from one season to the next. Sunset behaved the same way. Without realizing it, those early observers were watching Earth's journey around the sun. They could not know the true cause. They did not need to. Recognizing the pattern was enough. The changing position of sunrise announced the approach of warmer weather, colder weather, longer days, shorter days, and eventually another complete cycle of seasons. The moon revealed a different rhythm. Unlike the sun's gradual seasonal movement, the moon transformed itself every few nights in a way that anyone could follow. A thin crescent slowly grew into a brilliant full moon before shrinking once more into darkness. The entire cycle repeated with remarkable regularity. Unlike the changing seasons, the moon's rhythm unfolded quickly enough for one person to experience hundreds of complete cycles during a lifetime. It naturally became one of humanity's earliest ways of organizing longer stretches of time. The stars added another layer. Most stars seemed fixed relative to one another, yet the entire sky slowly rotated during the night before returning to familiar seasonal positions later in the year. Some constellations appeared only during certain months. Others disappeared below the horizon before returning exactly when expected. For people who depended directly upon nature, these recurring appearances were far more than beautiful sights. They became dependable signals. Certain stars announced approaching floods. Others coincided with seasonal migrations. Some appeared shortly before planting became possible. The heavens gradually became a calendar long before calendars existed. What makes this period so remarkable is that nothing was being measured yet. There were no numbers, no hours, no minutes, no carefully divided units. There was only comparison. People learned that one event reliably followed another. That relationship was enough to support increasingly complex decisions. Eventually, however, humanity experienced a transformation unlike anything that had come before. Groups that had spent countless generations moving across landscapes in search of food gradually began settling in one place. Agriculture did not spread everywhere at once, nor did it develop identically across the world. Different societies domesticated different plants and animals under different environmental conditions. Yet they all encountered the same fundamental challenge. Farming required planning. Seeds planted too early might freeze. Seeds planted too late might never mature. Harvesting before crops ripened reduced yields. Waiting too long risked losing everything to weather, insects, or disease. For hunters, nature could often be followed. For farmers, nature had to be anticipated. That distinction permanently changed humanity's relationship with time. Knowing what happened yesterday was no longer sufficient. Communities needed to know what would happen weeks and months into the future. The rhythms of the sky suddenly became more valuable than ever before. Across Mesopotamia, along the Nile, throughout East Asia, and in many other parts of the world, early farming societies reached remarkably similar conclusions despite developing independently. The heavens contained information. The sun announced the changing seasons. The moon provided shorter, recurring cycles. The stars revealed longer ones. The sky was not merely beautiful, it was useful. The more carefully people observed it, the more predictable life became. That realization quietly laid the foundation for one of humanity's greatest intellectual achievements. People began searching for ways to preserve those patterns so they could be shared reliably across entire communities instead of remaining only in individual memory. Observation alone was no longer enough. knowledge needed to become organized. That challenge would eventually lead to humanity's first calendars. Before anyone divided a day into hours, people first had to learn how to divide an entire year. Long before anyone built a clock, humanity solved a much larger problem. People learned how to organize entire years. Today, calendars are so deeply woven into everyday life that they almost disappear into the background. They quietly tell us when school begins, when taxes are due, when holidays arrive, when birthdays are celebrated, when contracts expire, and when the next season officially starts. We rarely stop to ask where this remarkable system came from, yet the invention of the calendar changed civilization just as profoundly as the invention of writing. Imagine trying to build a farming community without one. One village decides that spring has arrived because the weather feels warm enough. Another waits until the river begins to rise. A third plants after seeing the first blossoms appear on nearby trees. None of these methods is entirely unreasonable, yet none guarantees that neighboring communities will act together. A harvest festival might arrive before crops are ready. Religious ceremonies could slowly drift away from the seasons they were meant to celebrate. Taxes might be collected before farmers had gathered their grain. Trade would become increasingly difficult because different communities would struggle to agree where they stood within the year. As villages grew into towns and towns became cities, uncertainty itself became a problem. A successful civilization required something that everyone could share. The search for that shared system led people back to the sky. Among all the heavenly bodies, the moon appeared to offer the simplest solution. Unlike the stars, which demanded years of careful observation before their larger patterns became clear, the moon announced its cycle openly. Night after night, it changed shape before everyone's eyes. A slender crescent became a half-moon. The half-moon grew into a brilliant full moon, before slowly fading once again into darkness. Even a child could follow the pattern. It was nature's most obvious calendar. Many early societies naturally began counting time by lunar cycles. One new moon, then another, then another. Months were not invented by mathematicians. They were discovered through observation. Even today, that ancient connection survives in language itself. The English word month shares the same linguistic roots as moon, preserving a relationship that reaches back thousands of years. For relatively small communities, this approach worked surprisingly well. People could remember when an important event had happened by counting how many moons had passed since then. Hunters could estimate when familiar migration seasons would return. Families could plan ceremonies around predictable lunar phases. Religious traditions gradually aligned themselves with recurring nights in the lunar cycle. The moon provided order, but it also concealed a problem that revealed itself only after many years. Farmers began noticing something unsettling. A festival that had once welcomed spring slowly drifted toward winter. Planting ceremonies no longer matched the best planting season. Harvest celebrations gradually separated from the harvest itself. Nature had not changed. The calendar had. The reason lay in something no ancient observer could easily see. The moon and the sun follow different rhythms. A complete lunar cycle lasts a little less than 30 days. A complete cycle of seasons lasts a little more than 365 days. Those two rhythms refuse to fit neatly together. At first, the mismatch appears almost insignificant. A few hours here, a fraction of a day there. Yet those tiny differences accumulate year after year until the calendar slowly slips away from the seasons it was supposed to organize. Humanity had uncovered one of its earliest scientific puzzles. Nature was not governed by a single clock. Several clocks were operating at the same time, and they refused to stay synchronized. Different civilizations searched for different solutions. In Mesopotamia, generations of astronomer priests carefully recorded the movements of the moon, the sun, and prominent stars on clay tablets. Their observations stretched across centuries. No single lifetime could reveal the larger patterns, but many lifetimes working together could. This was one of humanity's earliest examples of cumulative science. Each generation inherited observations from the previous one instead of beginning again from nothing. Knowledge became stronger because it survived individual lives. Far to the southwest, Egyptian civilization confronted the same problem from a different direction. Life along the Nile depended upon one extraordinary event. Each year, floodwaters spread across the valley, covering fields with fertile silt before gradually retreating. Agriculture depended on preparing for that flood at exactly the right time. The sky offered an important clue. Shortly before sunrise on certain mornings each year, the bright star Sirius briefly appeared after weeks of invisibility. That first appearance closely coincided with the beginning of the Nile flood, making it one of the most valuable seasonal markers in the ancient world. Rather than relying primarily on the moon, Egyptian scholars increasingly organized their calendar around the yearly cycle of the sun. Their civil calendar approached 365 days, becoming one of history's earliest practical solar calendars. It was not perfect. Each year contained a small error that accumulated slowly across centuries. Even so, it represented a remarkable leap forward. For the first time, an entire civilization could plan agriculture, administration, taxation, and many religious observances around a calendar that remained closely connected to the changing seasons. Across East Asia, another solution gradually emerged. Instead of choosing between the sun and the moon, scholars developed increasingly sophisticated lunisolar calendars. Most years followed the lunar cycle, but additional months were occasionally inserted to keep the calendar aligned with the seasons. The methods differed. The challenge remained exactly the same. Every civilization was trying to reconcile several natural rhythms that refused to cooperate. The deeper people studied the heavens, the more complicated time became. The calendar transformed more than farming, it transformed power. Once a society depended on a shared calendar, someone had to decide when a new month officially began. Someone had to announce the new year. Someone had to determine the dates of festivals, taxes, legal obligations, military campaigns, and public ceremonies. Time was becoming political. The people who controlled the calendar gradually gained enormous influence because they controlled the rhythm according to which society operated. In many civilizations, this responsibility belonged to priests, royal astronomers, or government officials. Their authority rested not only on religion or tradition, but also on careful observation and accumulated knowledge. Understanding the sky increasingly meant governing the earth. For thousands of years, calendars remained among humanity's most valuable technologies. Unlike a tool or a weapon, they could not be held in one's hands. Yet, they organized agriculture, supported governments, regulated trade, defined religious life, coordinated labor, connected generations. A civilization could survive poor harvests, destructive floods, or difficult winters. Without a shared understanding of the year itself, however, maintaining order became far more difficult. Even today, the influence of those ancient calendars has never truly disappeared. Our modern calendar has been revised repeatedly through Roman reforms, the Julian calendar, and later the Gregorian calendar, adopted by much of the world. Yet beneath those refinements still lies the same ancient ambition that inspired the first skywatchers thousands of years ago: to bring order to recurring change. Calendars answered one enormous question: what day is it? Daily life, however, demanded another answer. Markets opened every morning. Courts held hearings. Workers gathered. Merchants arranged meetings. Religious ceremonies often began at carefully chosen moments. Knowing the day was no longer enough. civilization needed a way to divide the day itself into smaller, dependable pieces. Once again, humanity looked upward. This time the answer was waiting in the silent movement of a shadow across the ground. The first calendars solved one of civilization's greatest problems. They allowed entire societies to agree on the passage of years. Farmers knew when planting season was approaching. Governments could organize taxation and public works. Religious festivals returned at familiar moments. Merchants planned journeys months before setting out. But every sunrise brought a new challenge. A calendar could tell you that today was the right day to sow wheat. It could not tell you when today's work should begin. As villages became towns and towns grew into busy cities, daily life demanded increasing coordination. Markets needed opening hours, courts had to assemble witnesses, craftsmen promised to meet customers. Temple rituals often followed carefully prescribed moments throughout the day. The difference between early morning and late afternoon was no longer a matter of convenience. It affected trade, administration, religion, and eventually almost every organized activity within a growing civilization. For the second time in our story, humanity searched for an answer in the sky. The solution had been quietly present from the beginning. Every object standing beneath the sun casts a shadow. Trees, temple columns, walls, people, mountains. The shadows never remain still. As Earth rotates, they slowly change both their length and their direction. Morning shadows stretch across the ground. Near the middle of the day, they become much shorter. During the afternoon, they lengthen again while pointing toward a different part of the horizon. Most people probably accepted those changes without giving them much thought. A few careful observers noticed something extraordinary. Although clouds sometimes interrupted the pattern, the movement itself repeated with remarkable consistency. Whenever the sun occupied the same position in the sky, the shadow returned to nearly the same place. Another dependable rhythm had revealed itself. At first, no elaborate instrument was required. Imagine pushing a straight wooden pole into the ground. Return to that same pole several times during the day. Early in the morning, its shadow reaches far across the earth. As the sun climbs higher, the shadow steadily shrinks. Near the middle of the day, it becomes shorter than at any other moment. Then the process quietly reverses. The shadow grows longer once more until evening finally carries it into darkness. Nothing mechanical is happening, nothing artificial is involved. The earth itself is turning beneath the sky. The pole merely makes that invisible motion visible. Simple observations like these gradually evolved into one of humanity's earliest scientific instruments, the sundial. Its principle was almost beautifully simple. A fixed pointer, known today as a gnomon, cast a shadow across a carefully prepared surface. Marks placed at different positions allowed observers to recognize recurring portions of the day with increasing confidence. No gears moved. No springs released stored energy. No hidden mechanism counted passing moments. The planet itself supplied every movement. The dial simply translated that movement into something the human eye could read. Many civilizations developed their own versions independently. In ancient Egypt, some of the earliest known shadow clocks appeared thousands of years ago. Certain designs consisted of long bars marked with carefully measured divisions. During the morning, they pointed in one direction. Around midday, they were turned around so the afternoon shadow could continue, marking the passing hours. Elsewhere, increasingly sophisticated sundials appeared in temples, administrative centers, marketplaces, and public squares. Greek mathematicians later refined their geometry, discovering that the angle of the gnomon mattered enormously. Roman engineers carried sundials throughout an expanding empire, making them familiar features of urban life across much of the Mediterranean. As knowledge spread, so did accuracy. Yet every improvement revealed another layer of complexity. Suppose a traveler carried a carefully constructed sundial from Egypt to Greece. It would no longer keep time correctly. Nothing about the instrument had changed. The Earth had. More precisely, the traveler's position upon it had changed. The height of the sun above the horizon depends upon latitude. A sundial designed for one location cannot simply be placed hundreds of miles away and expected to produce identical results. The changing seasons introduced another complication. The sun follows a higher path across the summer sky and a lower one during winter. As a result, shadows behave differently throughout the year. A truly accurate sundial demanded far more than careful craftsmanship. It required astronomy, geometry, geography. What first appeared to be an ordinary stick casting a shadow gradually became one of humanity's earliest demonstrations that understanding time required understanding the structure of the world itself. This was an important turning point. Earlier generations had mainly observed recurring patterns. Now people were beginning to describe those patterns with increasing precision. Knowledge was becoming measurable. The effort invested in improving sundials also produced another unexpected consequence. People slowly became accustomed to dividing daylight into recognizable intervals. Before sundials, conversations naturally referred to broad parts of the day: morning, midday, evening. After generations of using shadow clocks, daily life became more finely organized. Work could begin after one portion of the shadow reached a familiar mark. A ceremony could wait until another. Meetings became easier to coordinate because communities shared visible reference points. The idea of the hour gradually entered everyday life. It did not yet resemble the hour we know today. In many ancient societies, daylight was divided into 12 equal parts regardless of the season. Because summer days were longer than winter days, a summer hour lasted longer than a winter one. To modern readers, this may sound inconvenient. To ancient people, it felt perfectly natural. Life itself expanded during long summer days and contracted during short winter ones. The clock reflected nature, rather than forcing nature to obey a mathematical definition. Only many centuries later would humanity insist that every hour remain exactly the same length throughout the entire year. Sundials quietly transformed architecture as well. Temples, monuments, and public buildings were often designed with careful attention to sunlight. Their orientation sometimes reflected astronomical knowledge accumulated over generations, blending practical observation with religious symbolism. The sky remained both a teacher and an authority. Yet even the finest sundial carried limitations that no amount of craftsmanship could eliminate. Clouds erased its shadow. Heavy storms made reading impossible. Most importantly, every evening the world's greatest clock disappeared beneath the horizon. Half of every day still belonged to uncertainty. Night guards needed to change shifts. Priests conducted ceremonies before dawn. Astronomers observed stars after sunset. Travelers sometimes departed while darkness still covered the landscape. The growing complexity of civilization demanded a clock that continued working even when the sun could no longer be seen. Humanity had learned to measure daylight. Now it faced a new challenge. Could time continue flowing inside a room, during a storm, or through the longest night of winter? The answer would emerge from something far more ordinary than sunlight. It would come from watching water fall, one steady drop at a time. Every evening, humanity's greatest clock disappeared. The sun slipped below the horizon. The shadows that had guided farmers, merchants, priests, and officials dissolved into darkness. The carefully marked lines of every sundial became useless until dawn returned. For thousands of years, this limitation was simply accepted. Daylight belonged to certainty. Night belonged to estimation. As civilization became more organized, estimation was no longer enough. Cities did not stop functioning after sunset. Temple rituals continued through the night. Guards changed shifts along city walls. Astronomers observed the stars before dawn. Physicians treated the sick. Merchants prepared caravans hours before sunrise. Someone needed to know how much of the night had already passed. The sun could no longer provide the answer. Humanity had to search for a different rhythm. This time, the solution would not come from the heavens. It would come from something much closer. Water. At first glance, water seems like an unlikely foundation for a clock. It never remains still. It splashes, freezes, evaporates, and changes its shape with every container that holds it. Yet careful observers noticed something remarkable. When water escaped through a very small opening, it often flowed at an almost steady rate. Not perfectly, but steadily enough to become useful. If the same amount of water left the same vessel in nearly the same amount of time, perhaps the flow itself could become a measure of passing hours. This idea represented a profound shift in human thinking. Until now, every major method of measuring time had depended on observing the natural world directly. People watched the sun cross the sky. They watched shadows move across the ground. Now they began creating an artificial process whose only purpose was to imitate nature's regularity. Instead of reading time, they were beginning to build it. The earliest water clocks, known today by the Greek name clepsydra, were surprisingly simple. Imagine a carefully shaped stone or ceramic vessel filled with water. Near its base, a tiny hole allowed the water to escape, drop by drop. Marks carved inside the container indicated how much water remained. As the water level slowly fell, each mark represented another portion of the night that had passed. Other designs worked in the opposite direction. An empty vessel filled gradually from another container, allowing the rising water to indicate the passing hours. The principle remained exactly the same. Time became visible through steady movement. Unlike the sun, flowing water continued beneath clouds. It continued inside buildings. Most importantly, it continued after sunset. For the first time, people possessed a practical way to divide both day and night using the same instrument. That achievement quietly transformed civilization. Ancient Egypt developed some of the earliest sophisticated water clocks, especially for religious use. Priests responsible for ceremonies performed before sunrise or during the night could no longer depend upon the position of the sun. Water provided a rhythm that remained available long after darkness had covered the land. Across Mesopotamia, similar devices helped organize temple life and astronomical observations. Careful records of the heavens often required knowing not only which night an event occurred, but also when during that night it appeared. Later, Greek engineers refined these designs, improving both their accuracy and their reliability. Although these civilizations differed greatly in language, culture, and religion, they were solving exactly the same problem. Every society experienced night. Every society experienced cloudy weather. Every society eventually reached the point where sunlight alone could no longer support an increasingly complex civilization. Water offered an elegant solution, yet it also exposed another difficult truth. Nature is never perfectly simple. The first water clock seemed remarkably reliable until people began comparing one with another. Cold weather slowed the movement of water. Warm weather increased evaporation. As the level inside a container gradually fell, the pressure pushing water through the opening changed as well. The first hour did not always pass at precisely the same speed as the last. These imperfections were small. They were also impossible to ignore. Something important had changed in humanity's relationship with time. Earlier generations had accepted whatever accuracy nature provided. Now people began asking a different question. How can we make the clock better? That question would drive nearly every major advance in timekeeping for the next 4,000 years. Ancient engineers experimented tirelessly. They changed the shape of vessels. They adjusted the size of openings. They searched for methods that kept water pressure more consistent as the container emptied. Generation after generation, they refined designs that had already existed for centuries. The clock itself became an engineering problem. Perhaps for the first time in history, precision became an objective rather than an accident. One of the greatest innovators in this tradition was Ctesibius of Alexandria, who lived during the 3rd century before the Common Era. His water clocks introduced sophisticated mechanisms that helped compensate for changing water pressure, making them considerably more accurate than many earlier designs. Some even incorporated floating indicators connected to gears, allowing the changing water level to move pointers automatically. These were no longer simple containers. They were becoming machines. Later inventors carried the idea even further. In parts of the ancient world, elaborate water clocks rang bells, opened small doors, moved mechanical figures, or sounded whistles as different hours passed. To modern eyes, these devices seem almost magical. To their creators, they represented something even more important: control. Human beings were learning how to regulate continuous motion with increasing precision. That knowledge would eventually influence machinery far beyond clocks. It would shape engineering itself. Water clocks also changed the meaning of time in quieter ways. In parts of the Greek and Roman world, courts sometimes measured legal speeches using flowing water. A speaker received only as much time as remained before the vessel emptied. The symbolism is difficult to miss. Time had become something that could be allocated, limited, regulated, distributed according to rules rather than sunlight. Today we speak naturally about spending time, saving time, wasting time, and giving someone more time. Those expressions feel completely ordinary. Their intellectual roots stretch much farther into history than many people realize. As societies became more organized, time gradually transformed from a natural phenomenon into a social resource. Governments managed it. Religious institutions organized it. Courts enforced it. Communities increasingly expected people to follow it. The clock was quietly becoming an instrument of civilization itself. Even so, water clocks never fully solved humanity's problem. Every vessel eventually emptied. Someone had to refill it. The mechanisms demanded regular maintenance. Cold weather, damaged containers, impurities in the water, and simple wear slowly reduced their reliability. Transporting them over long distances remained inconvenient. Perhaps most importantly, they still depended upon a resource that was constantly being consumed. Water flowed away. The clock stopped. The search continued. Across different civilizations, people experimented with burning candles, oil lamps, and sticks of incense, discovering that carefully controlled flames could also divide the passing hours. Each invention expanded humanity's understanding of time, yet none escaped the same fundamental weakness. Every one of them depended upon something that slowly disappeared. Water emptied, wax melted, oil burned, incense turned to ash. The ideal clock still remained beyond reach. People dreamed of a machine that could keep measuring time day after day without depending on sunlight, flowing water, or a burning flame. A machine whose rhythm came almost entirely from its own carefully controlled motion. Centuries would pass before that dream became reality. When it finally did, it would change far more than the history of clocks. It would reshape the rhythm of cities, the discipline of work, the authority of governments, and humanity's understanding of what it meant to live according to time itself. For thousands of years, every clock humanity invented depended on something that nature eventually took away. The sun disappeared below the horizon, water slowly drained from its vessel, candles burned down, oil lamps ran dry, incense turned to ash. Each invention solved one problem while leaving another behind. As civilizations expanded, that was no longer enough. Growing cities demanded something more dependable. Markets opened every morning, workshops operated throughout the day, courts followed increasingly regular schedules, religious communities observed fixed hours of prayer. Governments managed taxes, construction, and public administration across larger territories than ever before. The more organized society became, the more valuable, reliable timekeeping grew. People no longer needed only to measure time, they needed to trust it. That search gradually led to one of the most important technological revolutions in human history. Instead of asking how nature measured time, engineers began asking whether a machine could generate its own steady rhythm. It was an entirely new way of thinking. Earlier clocks observed natural processes. The next generation of clocks would regulate motion itself. The first steps toward that goal appeared gradually rather than all at once. Across medieval Europe, craftsmen experimented with weights, gears, wheels, and levers. Their work built upon centuries of mechanical knowledge inherited from earlier civilizations, including developments from the Islamic world, where engineers had designed remarkably sophisticated, water-powered automata and astronomical devices, as well as classical traditions preserved and expanded over generations. No single inventor suddenly created the mechanical clock. It emerged through the accumulated work of many anonymous craftsmen whose names history has long forgotten. By the High Middle Ages, one institution had become especially interested in improving timekeeping: the monastery. To a modern visitor, a medieval monastery might appear to be a place removed from technology. In reality, many monasteries depended upon careful organization. Monks followed structured daily routines that repeated throughout the year. Prayer, study, manual labor, meals, and sleep all occurred according to an established sequence. Several of those prayers took place before sunrise or long after sunset. Keeping that rhythm consistently was both a practical challenge and a spiritual responsibility. For centuries, monasteries relied upon sundials whenever daylight permitted, and upon water clocks or candles after dark. Those methods worked reasonably well. Eventually, reasonably well stopped being good enough. Clouds obscured shadows. Water clocks drifted. Candles burned unevenly. Every inaccuracy slowly accumulated. Communities that devoted their lives to disciplined routine naturally wanted something more dependable. The breakthrough came from gravity. Imagine suspending a heavy stone from a rope wrapped around a wooden drum. The moment you release it, gravity begins pulling the weight downward. That falling motion contains usable energy. The difficulty is obvious. Gravity works far too quickly. Without some way of controlling the descent, the weight would reach the ground in moments, ending the clock almost immediately. The entire problem became one of restraint. How could a machine release energy slowly instead of all at once? The answer appeared in one of the greatest inventions in the history of engineering: the escapement. Although modern clocks use many different forms of escapement, the basic idea remains remarkably elegant. Instead of allowing the weight to fall freely, the mechanism repeatedly interrupts its motion. A tiny amount of energy is released, then the movement stops. Another tiny amount follows, then another. The cycle repeats continuously. Each release advances the gears by a small, carefully controlled amount. For the first time, a machine possessed something resembling its own heartbeat. Tick, pause. Tick, pause. Tick. Every earlier clock had depended upon watching an external process unfold. The mechanical clock actively regulated its own movement. That distinction changed everything. During the late Middle Ages, large mechanical clocks began appearing in European churches, monasteries, and public buildings. Historians still debate which surviving examples deserve to be called the first true mechanical clocks, because the technology developed gradually across several regions rather than emerging from a single invention. What matters far more is what happened after they appeared. Cities embraced them. One tower after another, one church after another, one marketplace after another. Surprisingly, the earliest mechanical clocks often lacked something we now consider essential. They had no faces, no hands, no numbered dial. That sounds almost impossible to imagine because modern people think of clocks as objects that are meant to be seen. The first great tower clocks were built to be heard. Hidden high inside stone towers, their gears counted the passing hours before releasing a hammer that struck a great bell. The sound carried across rooftops and narrow streets. Merchants opening their shops heard it. Craftsmen working in their workshops heard it. Farmers approaching the city gates heard it. Travelers entering the town heard it. For perhaps the first time in history, thousands of people received the same signal at almost exactly the same moment. Time became public. This was one of the quietest revolutions in the history of civilization. Imagine growing up in a farming village where each family begins work whenever the sun seems high enough. Then imagine moving into a city where a bell announces the beginning of the working day, the opening of the market, the meeting of the town council, and the closing of the gates each evening. The difference extends far beyond convenience. The city itself begins functioning as a coordinated system. Commerce became easier to organize because buyers and sellers could expect markets to open together. Courts assembled more reliably. Public ceremonies became more orderly. Travelers gradually adjusted their routines to shared signals instead of personal judgment. The authority to announce time slowly shifted. For thousands of years, people had looked upward whenever they wanted guidance. Now they increasingly listened to machinery. This transformation also changed the way people thought. Time no longer belonged exclusively to nature. It was becoming an agreed social framework maintained by institutions. Churches rang the hours. City governments relied upon them. Guilds organized work around them. Daily life became increasingly synchronized. This growing discipline did not emerge overnight. It unfolded gradually across centuries. The historian David Lanz argued that mechanical clocks accomplished something far greater than improving timekeeping. They helped cultivate habits of regularity, punctuality, coordination, and disciplined labor that later became deeply connected with urban life, expanding commerce, and eventually industrial society. The clock did not create civilization by itself. It quietly changed the way civilization organized itself. Yet these remarkable machines remained imperfect. Even the finest medieval clock could gain or lose several minutes during a single day. Metal parts wore down. Temperature altered the behavior of components. Friction constantly stole energy from the mechanism. Every improvement exposed another opportunity for refinement. Engineers had solved the problem of creating a machine that could regulate its own motion. Now they faced a more demanding challenge. How could that motion become dramatically more precise? The answer would begin with an observation so ordinary that almost anyone could have noticed it. Inside an Italian cathedral, a gently swinging lamp traced graceful arcs through the air. Thousands of visitors probably glanced at it without another thought. One curious observer looked a little longer. That quiet moment would eventually transform every clock that followed. By the 14th century, mechanical clocks had changed Europe. Church bells marked the hours. Cities organized markets around shared schedules. Governments relied upon increasingly regular routines. Monasteries followed disciplined daily cycles with greater consistency than ever before. Compared with water clocks and sundials, the new machines were extraordinary. Compared with what would come next, they were astonishingly inaccurate. A well-built medieval clock could gain or lose several minutes each day. For everyday life, that was often acceptable. For astronomy, navigation, and the growing ambitions of science, it was not. Humanity had learned how to build clocks. Now it wanted clocks that could be trusted. The search for greater precision would begin with an observation so ordinary that almost anyone might have overlooked it. Around the end of the 16th century, A young student named Galileo Galilei was attending services in the Cathedral of Pisa. According to a story that later became famous, he noticed a large bronze lamp hanging from the ceiling. Whether someone had recently set it in motion or whether it had begun to sway naturally, the lamp moved gently back and forth through the air. Most people would have watched for only a moment. Galileo kept watching. As the swinging gradually became smaller, he noticed something unexpected. The lamp appeared to require nearly the same amount of time for each swing, even though the distance it traveled slowly decreased. He had no stopwatch. None existed. Instead, he compared the rhythm of the lamp with the beat of his own pulse. The comparison suggested that something remarkable was happening. The size of each swing changed. The time required for each swing changed very little. Modern physics shows that this is only approximately true. A pendulum remains nearly isochronous. That is, it swings in almost equal intervals for relatively small angles. Larger swings take slightly longer. Yet for the measurements available in Galileo's time, the effect was astonishingly regular. What mattered was not perfect accuracy. What mattered was discovering a natural motion far more consistent than anything clocks had previously used. Galileo immediately recognized the importance of the idea. If a pendulum repeated its motion so reliably, perhaps it could regulate a clock far better than the mechanisms already in use. He spent years studying pendulums, measuring how their motion depended upon length rather than weight. A heavier pendulum did not swing faster simply because it weighed more. Instead, the length of the pendulum largely determined its rhythm. Nature was revealing another hidden law. Galileo even sketched designs for a pendulum-regulated clock late in his life. He never completed one. The concept would wait for another brilliant mind. That mind belonged to Christian Huygens. Born in the Dutch Republic in 1629, Huygens grew up during one of Europe's great scientific flourishing periods. The 17th century witnessed rapid advances in astronomy, mathematics, optics, and mechanics. Telescopes revealed new worlds. Microscopes uncovered invisible life. Mathematical descriptions of nature became increasingly powerful. Accurate clocks had become one of science's greatest unsolved problems. In 1656, Huygens achieved the breakthrough. He designed the first successful pendulum clock. The principle itself was beautifully simple. Earlier clocks relied on mechanisms whose speed varied noticeably as friction changed or as driving weights slowly descended. Huygens attached those mechanisms to a pendulum whose steady rhythm controlled the escapement. Instead of the gears determining the pace, the pendulum dictated when each tooth could advance. The machine no longer hurried or hesitated as easily. It followed the pendulum's calm, repetitive motion. Tick swing, tick swing. For the first time, a clock possessed a regulator whose consistency approached the demands of serious science. The improvement was extraordinary. Mechanical clocks that had previously drifted by several minutes each day suddenly achieved accuracies measured in seconds. To modern readers, reducing an error from minutes to seconds may sound like a modest improvement. It was nothing of the sort. It represented an entirely different level of precision. Imagine a ruler that once measured only inches suddenly becoming accurate enough to distinguish individual grains of sand. That is roughly how dramatic the change felt to scientists of the 17th century. Astronomers immediately benefited. The positions of stars and planets could now be recorded with much greater confidence. Repeated observations became easier to compare. Small differences that had previously disappeared inside measurement errors gradually became visible. The clock was no longer merely serving astronomy. It had become one of astronomy's essential instruments. Navigation also stood to benefit. Determining latitude had long been relatively straightforward, because the height of familiar stars above the horizon could reveal how far north or south a ship had traveled. Longitude remained vastly more difficult. Sailors could estimate it by dead reckoning, combining speed, direction, and elapsed time, or under favorable conditions they could later use lunar distance methods developed in the 18th century. Yet all of these approaches were demanding, and accumulated errors often became dangerously large during long voyages. An accurate portable clock promised something revolutionary. If a navigator knew the precise time at a fixed reference location while also determining local solar time aboard the ship, the difference between those two times could reveal longitude. The mathematics was elegant. The engineering remained impossible. Pendulum clocks worked wonderfully inside buildings. Ships rarely behaved like buildings. Every wave altered the motion of the vessel. Every storm shook the mechanism. Every change in temperature subtly affected its components. A pendulum depends upon gravity acting in a stable direction. The rolling deck of a ship constantly changes that direction. The very invention that transformed science could not yet solve navigation's greatest problem. That challenge would eventually inspire one of history's most remarkable engineering achievements. For now, however, the pendulum transformed life on land. Clockmakers across Europe refined Huygens' design. Long pendulum clocks appeared in churches, observatories, universities, government buildings, and wealthy homes. Cases grew taller. Mechanisms became more intricate. Craftsmanship reached astonishing levels. The clock was becoming something more than a tool. It became a symbol. Owning an accurate clock demonstrated education, prosperity, and participation in an increasingly scientific world. More importantly, accurate clocks changed the way people thought about nature itself. If time could be measured with such consistency, perhaps motion could also be measured more precisely. Perhaps falling objects obeyed exact mathematical laws. Perhaps planets moved according to predictable rules. Perhaps the universe itself behaved like a system governed by discoverable principles. Precision in one instrument encouraged precision in every branch of science. The pendulum clock became part of a much larger intellectual transformation. Isaac Newton would later describe the motions of planets and falling bodies using mathematical laws whose testing depended increasingly upon reliable measurements. Across Europe, observatories compared observations, navigators improved charts, and scientists developed new experiments, all supported by clocks that grew steadily more dependable. The pursuit of accurate time was no longer simply about telling the hour. It had become part of humanity's effort to understand reality itself. Yet one enormous obstacle still remained: the world's oceans. A pendulum could regulate a clock with astonishing precision inside a quiet room. It became almost useless aboard a rolling ship crossing the Atlantic. Empires depended upon solving that problem. Trade depended upon solving it. Thousands of lives depended upon solving it. It would begin with disaster. By the beginning of the 18th century, humanity could build clocks of astonishing precision. Inside observatories, universities, and wealthy homes, pendulum clocks kept time more accurately than any previous machine. Astronomers measured planetary motions with increasing confidence. Scientists compared experiments performed hundreds of miles apart. Governments relied upon increasingly regular schedules. On land, the age of precision had begun. At sea, almost nothing had changed. The world's oceans remained among the most dangerous places on Earth. Storms could destroy entire fleets. Disease often claimed more sailors than combat. Navigation itself remained deeply uncertain once the coastline disappeared beyond the horizon. Experienced captains could usually determine latitude with reasonable accuracy by measuring the height of the sun at noon or familiar stars at night. Longitude was another matter entirely. Knowing how far east or west a ship had traveled was one of the greatest unsolved scientific and engineering problems of the age. The consequences were enormous. A navigational error of only a few degrees could place a vessel dozens or even hundreds of miles away from its intended position. Sometimes the mistake merely delayed a voyage. Sometimes it destroyed it. One tragedy became especially famous. In 1707, during the War of the Spanish Succession, Admiral Sir Cloudesley Shovel commanded a large British fleet returning home through difficult weather. Near the Isles of Scilly, southwest of England, navigational uncertainty contributed to a catastrophic disaster. 4 ships struck dangerous rocks, and well over 1,000 sailors lost their lives. For generations, this event has often been linked to the growing urgency of solving the longitude problem. Modern historians, however, caution against viewing the disaster as the single direct cause of later reforms. Concern over longitude had already been building across Europe for many years, driven by expanding trade, naval warfare, and exploration. The Scilly catastrophe became one powerful reminder of how costly navigational uncertainty could be, rather than the sole reason action was eventually taken. The underlying problem remained painfully clear. No one possessed a dependable way to determine longitude during long ocean voyages. Scientists already understood the basic principle. The Earth rotates once every 24 hours. That means it turns approximately 15 degrees every hour. If a navigator knew the exact time at a fixed reference location, such as London, and also determined local solar noon aboard the ship, comparing those 2 times would reveal the ship's longitude. The mathematics was surprisingly straightforward. The engineering seemed almost impossible. Imagine 2 perfectly synchronized clocks. Leave one safely in London. Carry the other aboard a ship crossing the Atlantic. Weeks later, observe the exact moment when the sun reaches its highest point above your ship. That marks local noon. If your portable clock still reads precisely 12 o'clock in London, then you have not changed longitude. If it reads 1 o'clock in the afternoon, your position differs by approximately 15 degrees of longitude. Every additional hour represents another 15 degrees. The entire solution depended upon one extraordinary requirement. The portable clock could not drift. Not by several minutes. Not even by a few seconds each day over months at sea. Every tiny error accumulated until the calculated position became dangerously wrong. Pendulum clocks, magnificent on land, failed almost immediately aboard ships. The vessel rolled continuously. Temperature changed from tropical heat to cold northern seas. Humidity expanded and contracted materials. Salt damaged delicate mechanisms. Gravity itself was no longer acting in a perfectly stable direction. Because the ship was constantly pitching and rolling, the pendulum could not provide the consistency required. Europe's greatest scientists searched for solutions. Some believed astronomy offered the answer. By carefully observing the changing positions of the moon against the background stars, a technique later known as the lunar distance method, experienced navigators could estimate Greenwich time without carrying a perfect clock. The method worked, but it demanded clear skies, excellent instruments, complicated calculations, and considerable mathematical skill. Others believed the future belonged to engineering. Build a clock that could survive the ocean. Many considered that dream unrealistic. One man refused to agree. John Harrison was not a famous mathematician. He was not a university professor. He was not even formally trained as one of Europe's leading scientists. He was a self-taught English carpenter with an extraordinary talent for solving mechanical problems. Working largely outside the scientific establishment, Harrison approached the longitude problem from a practical perspective. Instead of asking what theory demanded, he asked what the machine itself required. Over decades, he designed a remarkable series of increasingly sophisticated marine timekeepers. Each new model addressed weaknesses discovered in the previous one. He invented mechanisms that reduced friction. He experimented with materials that expanded less as temperatures changed. He developed ingenious systems that compensated for environmental variation long before modern precision manufacturing existed. His clocks did not emerge fully formed. They evolved through persistence. The process consumed much of his life. The first machines were enormous. Later versions became smaller, lighter, and dramatically more accurate. The culmination of this work, often known today as H4, resembled a large pocket watch rather than a traditional clock. During sea trials in the 1860s, during the early 1760s, including a celebrated voyage to Jamaica, it performed with astonishing precision, losing only a very small amount of time over the course of the journey. Its accuracy demonstrated something many experts had believed impossible. A portable mechanical clock could survive an ocean crossing. The achievement did not immediately end controversy. Harrison spent years defending his work before the British Board of Longitude, an organization established by Parliament in 1714 to encourage practical solutions to the longitude problem. Questions about testing, rewards, standards, and proof led to long disputes before Harrison eventually received much of the recognition he had earned. The story became as much about institutions as invention. Scientific breakthroughs rarely spread through brilliance alone. They also depend upon trust, verification, public acceptance, the willingness of established systems to embrace unfamiliar ideas. Eventually, marine chronometers based upon Harrison's pioneering work transformed navigation. Ships no longer relied solely on estimates accumulated day after day. Captains could determine longitude with increasing confidence. Ocean voyages became safer, trade became more predictable, navies operated more effectively across vast distances. Maps grew steadily more accurate. The consequences reached far beyond the sea. For the first time in history, precise portable time had become economically invaluable. A clock was no longer simply an instrument for monasteries, observatories, or wealthy households. It had become infrastructure. Commerce depended upon it, empires depended upon it, scientific exploration depended upon it. The search for longitude had quietly revealed a deeper truth. Accurate time was not merely convenient, it was geographic. Knowing where you were increasingly depended upon knowing exactly when you were. This idea would soon spread from the oceans onto land. Another technological revolution was already approaching. It would connect cities with iron rails and copper wires. Suddenly, keeping accurate time inside one town would no longer be enough. Entire nations would need to agree on the same hour. And that challenge would prove every bit as revolutionary as finding longitude across the sea. For thousands of years, time belonged to places. Every town kept its own noon. When the sun reached its highest point above the local horizon, the middle of the day had arrived. That simple rule worked remarkably well because neighboring villages lay only a few miles apart. The difference between their local times was so small that almost nobody noticed it. A traveler walking from one village to another would never realize that the sun reached its highest point a few minutes earlier in one place than in the next. The world moved slowly enough that nature's rhythm remained sufficient. Then transportation began moving faster than nature's differences could comfortably tolerate. During the 19th century, railways transformed travel. Journeys that had once required days by horse could suddenly be completed in hours. Cities became connected by expanding networks of iron rails stretching across entire countries. The railway solved one problem. It created another. Imagine boarding a train in one city shortly after noon. Several hours later, you arrive at your destination. According to your watch, it is 3 o'clock. According to the station clock, it is 2:52. Neither clock is broken, both are correct. The cities simply define noon differently because the sun reaches its highest point at different moments along different longitudes. For centuries, that difference had barely mattered. Railways made it impossible to ignore. Scheduling quickly became a nightmare. Every town followed its own local solar time, A timetable printed in one city became confusing almost immediately after the train crossed into another. Passengers missed connections. Freight arrived unexpectedly. Most importantly, railway companies struggled to ensure that trains traveling toward one another shared a common understanding of time. A mistake of only a few minutes could place two locomotives on the same stretch of track. The faster transportation became, the more dangerous disagreement became. Railway companies reached a conclusion that earlier generations had never needed to consider. Nature was no longer providing enough precision for modern society. Human beings would have to agree upon time. Not discover it, agree upon it. That distinction marked another turning point in our story. For thousands of years, clocks had attempted to imitate nature as faithfully as possible. Now nature itself became only part of the equation. Coordination required convention. Britain was among the first countries forced to confront this problem directly. As railway lines multiplied during the 1830s and 1840s, companies increasingly adopted the time kept at the Royal Observatory in Greenwich. Instead of adjusting every schedule to local solar noon, they synchronized operations using a single reference. This became known as Greenwich Mean Time. At first, many towns resisted. Church clocks often continued displaying local solar time, while railway stations displayed Greenwich time. Visitors sometimes found two different official times operating within the same town. One belonged to tradition, the other belonged to industry. For a while, both coexisted. Eventually, practicality prevailed. Keeping separate systems created confusion that grew more costly every year. The spread of the electric telegraph accelerated this transformation. Before telegraph networks, information traveled no faster than people, horses, or ships. A message sent to another city arrived hours or days later. Precise synchronization between distant locations was difficult because there was no rapid way to compare clocks. The telegraph changed that almost overnight. Electrical signals traveled across wires at extraordinary speed. Suddenly, observatories could transmit accurate time over vast distances. Railway stations hundreds of miles apart could synchronize their clocks far more reliably than ever before. Time itself began traveling through wires. This development produced an unexpected philosophical change. For countless generations, each community had relied primarily on its own sky. Now, an official time could arrive from somewhere else. A clock in one city increasingly trusted another clock hundreds of miles away, rather than the position of its own sun. Authority shifted once again. Not from priests to engineers this time. From local observation to national coordination. As industrialization accelerated, synchronized time spread beyond railways. Factories organized shifts around identical starting times. Banks coordinated financial activity. Postal systems became more reliable. Governments scheduled administration with increasing precision. Schools adopted standardized timetables. Entire societies gradually learned to move together. The historian E.P. Thompson later argued that industrialization transformed people's relationship with time itself. Earlier agricultural communities often organized work around tasks and natural conditions. Industrial production increasingly emphasized fixed schedules measured by the clock. Whether every occupation changed in exactly the same way is debated by historians, but there is broad agreement that industrial society greatly expanded the importance of punctual, standardized time. The clock was becoming more than an instrument. It was becoming a social contract. Yet one problem remained unsolved. Every country could standardize its own clocks. What happened when trains, ships, telegraph messages, and international trade crossed national borders? A traveler leaving Paris, entering regions using different local times. Ships sailing between continents encountered entirely different systems. Global commerce demanded something larger than national agreement. It required international agreement. In 1884, representatives from 25 nations gathered in Washington, D.C. for the International Meridian Conference. Their task was ambitious. They sought a common reference from which longitude could be measured and a shared prime meridian for navigation and mapping. After extensive discussion, the conference selected the meridian passing through the Royal Observatory at Greenwich as the international prime meridian. This decision built upon existing practice because many navigators and nautical charts already used Greenwich as a reference. The conference did not instantly create today's worldwide system of time zones, nor did every country adopt the recommendations immediately. Standard time developed gradually over subsequent decades as governments implemented national reforms. Even so, the meeting marked a decisive step toward the globally coordinated system we now take for granted. The modern map of time did not emerge from nature alone. It emerged from negotiation, from engineering, from politics, from commerce, from the growing realization that an interconnected world required shared conventions. Today, when you fly across continents, your phone quietly adjusts to a new time zone within moments. When financial markets open on opposite sides of the planet, computers coordinate events separated by thousands of miles. International flights, satellite communications, internet traffic, weather forecasting, emergency services, and global business all depend upon billions of devices agreeing on time with extraordinary precision. Most of us never notice this invisible cooperation. It has become ordinary. Yet beneath every synchronized schedule lies a decision made by generations of scientists, engineers, railway planners, astronomers, diplomats, and governments who gradually transformed countless local times into one coordinated global framework. It would have been tempting to believe that humanity had finally solved the problem of time. The clocks agreed, the railways ran, the telegraphs synchronized nations. The world appeared more orderly than ever before. Then physicists began measuring time with even greater precision. The results were deeply unsettling. The clocks were not disagreeing because they were poorly built. They were disagreeing because time itself refused to behave exactly as anyone had imagined. The next revolution would not come from engineers. It would come from Albert Einstein. By the end of the 19th century, humanity had achieved something that would have seemed almost miraculous only a few generations earlier. Railway stations synchronized their clocks. Telegraph operators transmitted precise signals across continents. Observatories compared measurements made hundreds of miles apart. International trade depended upon agreed schedules. The world appeared to share a single rhythm. Most scientists believed the remaining challenge was simply improving accuracy. Build better clocks, reduce mechanical errors, measure ever smaller fractions of a second. Time itself seemed completely understood. It flowed evenly. It flowed everywhere. It flowed for everyone. Or so it appeared. Hidden beneath that confidence was a puzzle that had been troubling physicists for decades. Light behaved strangely. For centuries, people had assumed that motion worked the same way for everything. Imagine standing beside a road. A carriage passes at 10 miles per hour. If another carriage traveling 5 miles per hour moves in the same direction, the first carriage appears to pull away at only 5 miles per hour. This feels completely natural. Relative motion surrounds us every day. Throw a ball forward while walking. Its speed relative to the ground becomes the speed of your walk plus the speed of the throw. The faster you move, the faster the ball travels relative to someone standing still. For ordinary objects, this simple reasoning works remarkably well. Physicists naturally expected light to behave the same way. If a lamp shines from a moving train, shouldn't someone standing beside the tracks measure a different speed than a passenger riding inside? Nature answered differently. Repeated experiments suggested that everyone measured the same speed of light, regardless of how they were moving relative to the source. The most famous investigation came in 1887, when Albert A. Michelson and Edward W. Morley performed an extraordinarily sensitive experiment designed to detect Earth's motion through the hypothetical luminiferous ether, a substance many physicists believed filled all of space and carried light waves. They expected to find evidence that Earth's motion affected the measured speed of light. They did not. The result became one of the greatest surprises in the history of physics. The experiment did not immediately destroy belief in the ether. Many scientists proposed increasingly complicated explanations to preserve the existing picture of reality. For years, the mystery remained unresolved. Then, in 1905, a young patent examiner working in Bern published a paper that changed physics forever. Albert Einstein was only 26 years old. He did not begin by inventing complicated mathematics. He began by asking an unusually simple question: what if the experiments were correct? Instead of trying to explain why the speed of light appeared constant, Einstein asked what would happen if it really were constant for every observer. The consequences were astonishing. Space could no longer remain exactly the same for everyone. Neither could time. Einstein built his theory upon two remarkably simple postulates. First, the laws of physics are the same in every inertial frame of reference. No observer moving at constant velocity occupies a privileged position from which the universe behaves differently. Second, the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. Those two ideas sound almost harmless. Together, they forced scientists to abandon centuries of intuition. Imagine two observers. One stands beside a railway track. The other sits inside a train moving at tremendous speed. A flash of light appears inside the train exactly halfway between its front and back. To the passenger, the light reaches both ends simultaneously because both ends are equally far away. To the observer standing beside the tracks, the situation looks different. While the light travels, the front of the train moves away from the approaching light, while the rear moves toward it. Since both observers must measure the same speed of light, they cannot both agree that the flashes arrive simultaneously. One observer sees simultaneous events, the other does not. Neither is mistaken. Simultaneity itself depends upon the observer's state of motion. This idea was so profoundly unfamiliar that even many physicists struggled to accept it. For thousands of years, people had assumed that now meant the same thing everywhere. Einstein demonstrated that nature does not always agree. Events that appear simultaneous for one observer may occur in a different order for another moving observer. Time had lost its universal meaning. The consequences continued. If observers moving relative to one another disagreed about simultaneity, they would also disagree about the amount of time separating events. Time itself became elastic. This phenomenon is known as time dilation. Contrary to popular imagination, nothing inside the moving clock slows down because of mechanical failure. Every process slows together. A pendulum swings more slowly. Chemical reactions proceed more slowly. Electronic circuits oscillate more slowly. Even biological aging slows by the same amount. The clock is not malfunctioning. Time itself passes differently along different paths through space-time. The effect is extraordinarily small at everyday speeds. Walk across your living room, drive across a country, fly around the world. The difference amounts to tiny fractions of a second, far too small for human senses to notice. Yet the effect is absolutely real. Scientists have measured it repeatedly using extremely precise atomic clocks carried aboard aircraft, satellites, and spacecraft. The predictions agree with observation to astonishing accuracy. This was no longer philosophy, it was measurable physics. Einstein's theory also revealed another remarkable relationship. Space and time could no longer be treated as separate entities. Earlier generations imagined space as the stage upon which events occurred, while time flowed independently in the background. Special relativity united them into a single framework, now called space-time. Every event possesses both a location and a time. Neither can be completely separated from the other. This new picture of reality solved puzzles that had troubled physicists for years. It also raised entirely new questions. If motion could change the passage of time, what about gravity? Isaac Newton had described gravity as a force acting between masses. Einstein suspected something deeper. He spent the next decade searching for a new explanation. In 1915, he found it. General relativity proposed that gravity is not simply a force pulling objects together. Mass and energy change the geometry of space-time itself, and objects move along the curved paths created by that geometry. One astonishing consequence followed naturally. Gravity also changes the passage of time. A clock closer to a massive object ticks slightly more slowly than a clock farther away. The difference is unimaginably small near Earth's surface. It is also real. Every modern GPS satellite experiences both special relativistic and general relativistic effects. Because the satellites move rapidly, special relativity causes their onboard clocks to run slightly slow. Because they orbit far above Earth's surface, where gravity is weaker, general relativity causes those same clocks to run slightly fast by an even larger amount. Engineers account for both effects so that the system continues providing accurate positioning. Without those corrections, GPS errors would accumulate rapidly, eventually growing by several miles each day. Your phone does not mention Einstein whenever you request directions. Nevertheless, every successful navigation quietly confirms his theories. Perhaps the most surprising lesson is not that time changes. It is that humanity discovered this by building increasingly accurate clocks. Every improvement in timekeeping revealed another layer of reality. The better we became at measuring time, the stranger time itself appeared. Yet even Einstein's astonishing discoveries did not mark the end of the story. Scientists still depended upon clocks built from gears, springs, and carefully engineered mechanisms. They were magnificent instruments. They were not perfect. Somewhere inside nature existed an even more reliable rhythm. Finding it would require looking beyond pendulums, beyond springs, beyond machinery itself, and into the heart of the atom. Einstein had transformed humanity's understanding of time. He showed that time does not pass identically everywhere. Motion changes it. Gravity changes it. The universe itself proved to be far stranger than anyone had imagined. Yet Einstein's discoveries depended upon something remarkably ordinary. Clocks. The better scientists measured time, the more clearly nature revealed its hidden laws. That realization inspired a new question. How accurate could a clock become? For centuries, every improvement had followed the same pattern. Clockmakers built better gears, reduced friction, improved springs, designed more stable pendulums, crafted finer escapements. Each generation made the previous one seem crude. Eventually, however, engineers encountered a fundamental limit. Every mechanical clock is made from physical objects. Metal expands and contracts as temperature changes. Lubricants age. Springs slowly fatigue. Bearings wear down. Even the finest craftsmanship cannot completely eliminate these effects. The search for greater precision required abandoning traditional machinery altogether. Scientists began searching for a rhythm that nature itself repeated with extraordinary consistency. They found it inside the atom. At first, this idea sounds almost impossible. Atoms are unimaginably small. How could something invisible become the world's most accurate clock? The answer emerged during the 20th century as physicists developed quantum mechanics. Unlike planets, pendulums, or mechanical gears, atoms occupy discrete energy states. They cannot possess just any amount of energy. Instead, electrons within an atom may exist only in specific allowed states. When an atom changes from one energy state to another, It absorbs or emits electromagnetic radiation at an extremely specific frequency. This frequency is not chosen by the engineer, it is determined by the laws of nature. Every atom of the same isotope behaves identically under the same conditions. That remarkable consistency suggested an extraordinary possibility. Instead of building a clock around moving gears, build one around a natural frequency that never needs to be invented, only measured. Scientists explored several possibilities before discovering that one isotope proved especially useful: cesium-133. When cesium atoms are carefully prepared under controlled conditions, they can undergo a particular transition between two hyperfine energy levels of their ground state. The electromagnetic radiation associated with this transition has an extraordinarily stable frequency. This was exactly the rhythm physicists had been searching for. Unlike a pendulum, it does not depend on length. Unlike a spring, it does not weaken through repeated use. Unlike a gear, it does not wear down. The atom itself provides the reference. Modern atomic clocks operate through a beautifully elegant principle. Turning point in our story. The earliest clocks observed the sun. Later clocks regulated mechanical motion. Atomic clocks measured one of the most stable natural processes known to physics. Humanity had come full circle. Nature had once again become the ultimate authority. Only now it was no longer the movement of stars. It was the behavior of matter itself. The improvement in precision was almost beyond comprehension. A good pendulum clock might lose a second every day. Modern cesium atomic clocks can operate for millions of years before accumulating an error of roughly 1 second under ideal conditions. Newer optical atomic clocks being developed in research laboratories are even more stable, reaching levels of precision that would have seemed unimaginable only a few decades ago. Those numbers are difficult for the human mind to grasp. Imagine starting an ideal clock long before the construction of the Egyptian pyramids. A modern atomic clock would still be extraordinarily close to the correct time today. Such precision transformed science. Astronomers could compare observations across continents with unprecedented confidence. Physicists measured tiny effects predicted by relativity. Engineers synchronized communication networks operating across the globe. Entire branches of research became possible because time itself could now be measured so precisely. The impact extended far beyond laboratories. International telecommunications depend upon synchronized timing. Financial systems rely on precise timestamps to establish the sequence of transactions. Electrical power grids coordinate vast networks spanning entire countries. Scientific observatories compare measurements made on different continents. Spacecraft navigate millions of miles from Earth. Every one of these systems depends upon clocks agreeing with extraordinary precision. Most people never notice. The synchronization happens silently, every second, every day. The definition of the second itself eventually changed. For much of history, a second had been defined indirectly through Earth's rotation and astronomical observations. Unfortunately, Earth's rotation is not perfectly uniform. Tiny variations occur because of complex interactions involving Earth's interior, oceans, atmosphere, and even the gravitational influence of the Moon and the Sun. Those variations are extremely small. For modern science, they mattered. In 1967, the international scientific community adopted a new definition. The second was redefined as the duration of 9,192,631,770 periods of the radiation corresponding to the transition between the two hyperfine levels of the ground state of the cesium-133 atom. It is an intimidating sentence. Hidden inside it lies one of history's greatest conceptual changes. Humanity no longer defined time by watching the heavens. It defined time by counting the behavior of atoms. The sky had guided civilization for thousands of years. Now the atom had become the world's most trusted clock. Yet an unexpected irony remained. The more accurately scientists measured time, the more they discovered that perfect synchronization was impossible. Einstein had already shown that clocks moving differently or experiencing different gravitational fields cannot all tick at exactly the same rate. Atomic clocks confirmed those predictions with astonishing precision. Even clocks, separated by modest differences in altitude, experience tiny differences in the passage of time because gravity changes slightly with height. The effect is extraordinarily small. It is also measurable. In a sense, the world's greatest clocks spend every moment reminding us that time is not absolute. The quest for perfect precision ended by revealing that nature itself refuses to provide a single universal rhythm. Perhaps that is the most remarkable lesson in the entire history of timekeeping. Every generation believed it was approaching the final answer. Every improvement uncovered a deeper question. Humanity began by watching shadows move across the ground. It ended by measuring the quantum behavior of atoms, and still, the mystery of time remains unfinished. After thousands of years of observation, invention, and discovery, it is tempting to believe that humanity has finally conquered time. Our clocks lose almost nothing. Satellites remain synchronized. Global communication depends upon billions of perfectly coordinated electronic systems. A message travels across oceans in moments. An aircraft crosses continents, while computers continuously correct its position. Financial markets execute transactions separated by millionths of a second. Compared with every civilization that came before us, we seem to live in an age where time has been completely mastered. Yet appearances can be deceptive. The more precisely humanity learned to measure time, the more mysterious time itself became. This strange pattern has repeated throughout our story. Early observers believed the sky simply repeated familiar cycles. Then they discovered calendars. Calendar makers believed the year could be divided into neat patterns. Then they encountered competing rhythms of the sun and the moon. Mechanical clockmakers believed precision was only a matter of better engineering. Then pendulums revealed new possibilities. Pendulum clocks appeared to solve accuracy itself. Then relativity demonstrated that different clocks naturally disagree. Atomic clocks promised nearly perfect stability. They ended up confirming that time flows differently depending on motion and gravity. Every solution uncovered another question. Perhaps that should not surprise us. Human beings have never observed time directly. We have always observed change. A shadow moving across the ground, water flowing from a vessel, a pendulum swinging through the air, an atom changing between energy states, the movement of planets, the vibration of quartz, the oscillation of electromagnetic radiation. Every clock, no matter how sophisticated, measures a process that repeats with extraordinary regularity. Time itself remains invisible. This distinction may seem subtle, it is actually profound. Suppose every physical process in the universe suddenly slowed by exactly the same amount. Every heartbeat, every chemical reaction, every atomic vibration, every pendulum, every electronic circuit, every biological process. Would anyone notice? Probably not. Every clock would slow together. Every observer would experience the same rhythm. Nothing inside the universe would provide a comparison. This thought experiment illustrates why physicists often describe time through relationships between events, rather than as an independent substance flowing around us. Exactly what time ultimately is remains one of the deepest unanswered questions in physics. Quantum mechanics and general relativity both describe nature with extraordinary success, yet they describe time in strikingly different ways. In Einstein's general relativity, space-time forms part of the geometry of the universe itself. Gravity changes that geometry. Time becomes woven together with space. In quantum mechanics, however, time often appears as an external parameter, against which quantum systems evolve. Reconciling these two pictures remains one of modern physics' greatest challenges. Researchers investigating quantum gravity continue exploring whether time is fundamental or whether it emerges from something even deeper. No consensus has yet been reached. Some proposals suggest that time may arise from relationships between quantum systems rather than existing independently. Others treat space-time itself as something that emerges from more fundamental physical structures. These ideas remain active areas of research rather than established scientific conclusions. Remarkably, after thousands of years of increasingly precise measurements, humanity still cannot answer one deceptively simple question with complete confidence. What is time? Perhaps that uncertainty is not a sign of failure. It may instead reflect how science progresses. The purpose of science has never been to eliminate mystery. Its purpose is to replace smaller mysteries with larger, better questions. The history of time illustrates this beautifully. Ancient sky watchers asked when the river would flood. Astronomers asked how planets moved. Navigators asked where they were on the ocean. Engineers asked how to build more accurate clocks. Physicists asked whether time itself could change. Today's researchers ask whether space-time emerges from quantum reality. Every generation inherits questions that the previous generation made possible. This long history also changes the way we see ordinary life. Tomorrow morning, an alarm clock may wake you. You might check the time on your phone before getting out of bed. A calendar reminds you about a meeting. Navigation software estimates your arrival. A smartwatch quietly records your heartbeat. None of these actions feels extraordinary, yet every one of them carries the accumulated knowledge of thousands of years. Behind a single number displayed on a screen stand Egyptian priests observing Sirius, Babylonian astronomers recording the moon, Greek mathematicians refining geometry, medieval craftsmen building gears, Galileo studying a swinging lamp, Huygens perfecting the pendulum, John Harrison solving the longitude problem, railway engineers synchronizing nations, Einstein redefining time itself. Modern physicists measuring atoms with astonishing precision. Their work surrounds you every day. It arrives so quietly that it has become almost invisible. Perhaps that is the greatest success in the history of timekeeping. The most transformative technologies eventually disappear into ordinary life. Electricity rarely astonishes us. Written language rarely amazes us. Running water, refrigeration, and wireless communication quickly become expectations rather than miracles. Timekeeping followed the same path. Humanity spent thousands of years searching for reliable time. Today, most of us carry clocks more accurate than those used by the greatest observatories of previous centuries, without giving them a second thought. The journey that began beneath an open sky has not truly ended. Every improvement in timekeeping has expanded humanity's understanding of the universe. Every improvement has also revealed how much remains unknown. Perhaps future generations will build clocks beyond anything we can currently imagine. Perhaps they will discover that time emerges from principles still hidden from modern science. Perhaps they will rewrite everything we currently believe. History suggests they probably will. Because throughout this entire story, one lesson has remained remarkably consistent. Humanity never stopped measuring time. Time never stopped surprising humanity. And somewhere, at this very moment, an atomic clock is quietly counting invisible transitions inside a cloud of atoms. Satellites are correcting for the curvature of space-time above your head. Earth continues turning beneath your feet. And the universe keeps unfolding exactly as it has for billions of years, whether anyone is watching or not. By now, our story has followed humanity from the first observations of the sky to the astonishing precision of atomic clocks. Yet one surprisingly familiar question has remained almost invisible. Why does a day contain 24 hours? Why does every hour contain 60 minutes? Why does every minute contain 60 seconds? Modern life depends upon these numbers so completely that they rarely seem unusual. Children learn them before they understand where they came from. Clocks display them. Computers count them. Airlines schedule around them. Hospitals record them. Scientists measure them to extraordinary precision. Most of us assume those numbers simply belong to nature. They do not. They belong to history. Imagine that you have been transported back 4,000 years. Someone asks you how long an hour lasts. You cannot answer. Not because you have forgotten, because the question itself makes very little sense. The concept of an hour, as we understand it today, does not yet exist. People certainly recognize morning, midday, evening, and night. They recognize seasons. They recognize lunar months. But dividing every day into exactly 24 equal portions is still an idea waiting to emerge. Its origins lie in one of humanity's oldest mathematical traditions, ancient Mesopotamia. Between the Tigris and Euphrates rivers, generations of Babylonian scholars developed an approach to mathematics unlike the decimal system most of us use today. Instead of counting primarily in groups of 10, they often counted in groups of 60. At first glance, 60 seems like a strange choice. 10 appears much simpler. We have 10 fingers. Children naturally learn to count with their hands. Why would anyone prefer 60? The answer becomes clearer the moment you begin dividing it. 10 divides cleanly only by 2 and 5. 60 divides evenly by 2, 3, 4, 5, 6, 10, 12, 15, 20, 30. For astronomers, surveyors, merchants, and mathematicians, this flexibility proved extraordinarily useful. Fractions that become awkward in a decimal system often remain beautifully simple within a base 60 system. 1/2, 1/3, 1/4, 1/5, 1/6. Each can be expressed without endless repeating fractions. That practical advantage helped Babylonian mathematics survive for centuries. The Babylonians did not invent time itself. They invented an exceptionally convenient way to organize numbers. That mathematical inheritance would eventually spread far beyond Mesopotamia. Astronomy played an important role. Babylonian astronomers spent centuries recording the motions of the sun, moon, and planets with remarkable care. Their observations influenced later scholars throughout the ancient Mediterranean, particularly Greek astronomers, who inherited both data and mathematical techniques. Knowledge rarely remains confined to one civilization. It travels, sometimes through trade, sometimes through conquest, sometimes through translation. Ideas migrate almost as reliably as people do. Over generations, Babylonian mathematics became woven into the developing science of astronomy. Meanwhile, another tradition was emerging along the Nile. Ancient Egyptians had long divided daylight into 12 parts using shadow clocks and other observational methods. Night was also organized into 12 intervals, originally linked to groups of stars known today as decans that rose successively throughout the darkness. These ancient systems did not produce 24 equal hours throughout the year. Summer daylight lasted longer than winter daylight. Night changed in the opposite direction. An hour during midsummer differed from an hour during midwinter. To ancient observers, this felt perfectly reasonable. Nature itself changed. Why shouldn't ours change with it? Only much later did astronomers begin combining these traditions into a more uniform system. Gradually, the familiar structure emerged. 12 portions of daylight, 12 portions of darkness. Together, 24 hours. The number was never inevitable. Human history could easily have taken another path. During the French Revolution, reformers briefly attempted to decimalize time itself. Days were divided into 10 hours, each hour into 100 minutes, and each minute into 100 seconds. On paper, the system appeared elegant. In practice, it failed. Generations had already organized their lives around older traditions. Every clock required redesign. Every timetable required revision. Every habit demanded replacement. The benefits proved too small to outweigh the enormous disruption. Within only a few years, decimal time largely disappeared. The older system survived, not because nature demanded it, because history had already chosen it. The same story applies to minutes and seconds. The hour was eventually divided into 60 minutes, each minute into 60 seconds. Early astronomers often described these as the first small division and the second small division of an hour. From those Latin expressions eventually emerged the modern word second. Every glance at a wristwatch quietly preserves vocabulary created centuries ago. One of history's most remarkable characteristics is its persistence. Ideas survive. Long after kingdoms vanish, long after languages change, long after the people who created them have disappeared. Every digital clock displaying 12:37 or 8:45 still carries mathematical decisions made thousands of years ago. The Babylonians could never have imagined satellites orbiting Earth. They could never have imagined smartphones or computers or atomic clocks. Yet every one of those technologies still counts time using numbers their civilization helped popularize. This is one of the quietest forms of continuity in human history. Empires rise, empires fall. Religions spread, languages evolve. Scientific theories are replaced. Still, the hour remains 60 minutes. The minute remains 60 seconds. The rhythm survives. Perhaps even more remarkable is what those numbers reveal about civilization itself. Technology rarely begins from nothing. Each generation inherits tools created by countless earlier generations. Sometimes those inheritances are obvious. Roads, buildings, books. Sometimes they are invisible. The way we write numbers. The way we divide circles into 360 degrees. The way we measure angles. The way we measure time. We imagine ourselves living in a thoroughly modern world. In reality, fragments of ancient civilizations accompany us every moment of every day. Every appointment at 3 o'clock, every countdown before a rocket launch, every stopwatch timing an Olympic race, every timestamp attached to a photograph. Each quietly echoes decisions made by people who watched the skies thousands of years before the invention of electricity. By now, humanity had learned how to divide years, then days, then hours, then minutes, eventually even seconds. But measuring time was only part of the story. An equally important question remained. Who decided when those hours should be used? Who determined when people should wake, pray, work, or rest? The next chapter is not about mathematics, it is about authority. Because before clocks disciplined factories, they first disciplined monasteries. Long before factories demanded punctual workers, long before railways synchronized nations, long before governments standardized clocks, there was another institution that required regular timekeeping every single day: religion. For much of human history, religious life followed rhythms that repeated with remarkable consistency. Ceremonies, festivals, sacrifices, fasts, prayers, and processions all depended upon knowing not only which day had arrived, but often which part of the day as well. The desire to organize sacred time became one of the most powerful forces driving the history of clocks. This connection appeared far earlier than many people realize. In ancient Egypt, priests observed the stars before dawn to determine when important rituals should begin. The annual appearance of Sirius helped announce the coming inundation of the Nile, linking astronomy directly to both agriculture and religion. In Mesopotamia, temple astronomers spent generations recording the motions of the heavens. Their observations were practical, scientific, and religious all at once. The sky was not merely something to admire, it was a source of order. Across many cultures, calendars determined the dates of sacred festivals. Lunar cycles marked important celebrations. Solar cycles determined others. Understanding the heavens became part of maintaining harmony between society, nature, and the divine. Yet nowhere did daily timekeeping become more disciplined than inside medieval monasteries. Imagine entering a Benedictine monastery around the 11th century. Life unfolds with astonishing regularity. Before sunrise, bells summon the community from sleep. Hours later, another bell calls everyone back for prayer. Work follows, study follows, meals follow. Silence returns. Then another prayer, then another, then evening, then night. Tomorrow the entire sequence begins again. The purpose was not efficiency in the modern economic sense, it was devotion. The Rule of St. Benedict, written during the 6th century, described a carefully ordered monastic life structured around prayer, work, reading, and rest. While individual monasteries differed in their practices, many organized the day around a sequence of canonical hours that guided communal worship. These hours included matins during the night, followed by lauds at dawn, prime in the early morning, terce, sext, and none throughout the day, then vespers during the evening and compline before sleep. To modern ears, the names sound unfamiliar. The underlying idea does not. Life itself could be organized through recurring moments shared by an entire community. Keeping those moments accurately mattered. At first, monasteries relied upon sundials whenever sunlight allowed. Water clocks helped after dark. Candles marked passing hours during long winter nights. Each method carried limitations. Clouds obscured shadows, water clocks drifted, candles burned unevenly. Monastic life demanded greater consistency than these methods could always provide. This practical need encouraged the adoption and improvement of mechanical clocks. Historians continue debating exactly where the earliest mechanical clocks first appeared. What is clear is that monasteries became among their earliest and most enthusiastic users. The reasons were straightforward. A reliable clock meant the community no longer depended until weather or seasonal daylight. Prayer could begin at predictable times throughout the year. Daily life became increasingly synchronized. The sound of bells spread that synchronization beyond monastery walls. Villagers working nearby heard them. Travelers passing along roads heard them. Merchants entering town heard them. Even people who never entered the monastery gradually organized portions of their own day around those familiar sounds. Without intending to do so, religious communities helped teach entire towns to live by the clock. Church bells gradually became the public voice of time. Before most people owned clocks, they heard them. A single bell ringing across rooftops informed thousands of people simultaneously. Morning had begun. Midday had arrived. Evening approached. The gates would soon close. Prayer would soon begin. The bell transformed invisible time into a shared experience. This influence extended far beyond Europe. In the Islamic world, daily life also followed recurring moments of worship. Muslims pray 5 times each day, with each prayer associated with the position of the sun rather than fixed clock times. For centuries, determining these moments required careful astronomical observation. Scholars developed sophisticated methods for calculating prayer times, constructing instruments, and refining astronomical tables. Mosques often employed specialists responsible for determining the appropriate times for prayer. Astronomy flourished, partly because religious life demanded accuracy. The same pattern appeared elsewhere. Across South Asia, Hindu rituals frequently followed carefully chosen lunar dates and astronomical alignments. Jewish religious life depended upon a lunisolar calendar, requiring detailed calculations to determine festivals throughout the year. Buddhist communities likewise organized many observances around recurring lunar cycles. Different religions reached different conclusions about theology. They often shared one practical reality: sacred life required reliable knowledge of recurring time. This relationship between religion and time reveals something important about civilization. People did not first invent clocks because they were fascinated by precision. They invented better clocks because communities depended upon regularity. Prayer required it, agriculture required it, government required it, trade required it. Every improvement answered a human need before it became a scientific achievement. Over time, however, something subtle began changing. The bells still rang, the prayers still continued. But cities grew larger, markets expanded, universities welcomed students, guilds organized skilled labor, merchants crossed continents. Time slowly acquired new responsibilities. It still belonged to religion, it also belonged increasingly to commerce. A merchant waiting for a customer cared about the hour. A craftsman delivering an order cared about the hour. A university lecturer beginning a lesson cared about the hour. Society itself was becoming more dependent upon synchronized routines. Religion had helped teach civilization to respect regular time. Another institution would soon demand something even stricter. Not prayer, but productivity. Not devotion, but efficiency. The bells that once called monks to worship would eventually be joined by whistles calling workers to factories. The discipline of sacred time would become the discipline of industrial time. And that transformation would reshape the modern world more profoundly than almost anyone could have imagined. For thousands of years, time helped people understand nature. Then it helped organize religion. Eventually, it began organizing work itself. This transformation did not happen overnight. For most of human history, work followed tasks rather than clocks. Imagine a farming family several centuries before the Industrial Revolution. The day begins when daylight becomes strong enough to see. People work until the heat grows too intense. They pause, then they continue. If rain arrives, work changes. If harvest season comes, everyone labors from dawn until darkness. If winter shortens the day, the schedule shortens with it. The work determines the rhythm, the clock merely observes. Historians sometimes describe this as task-oriented time. The goal is not to work until a particular hour. The goal is to finish the task. Harvest the field, repair the roof, bake the bread, bring the sheep home. Nature decides the pace, human beings adapt. Even skilled craftsmen often worked in similar ways. A blacksmith completed an order. A mason finished part of a wall. A carpenter built a table. The quality of the work mattered more than the precise minute when it ended. This did not mean people ignored time. Quite the opposite. Farmers understood seasons with remarkable precision. Merchants arranged meetings, cities rang bells, monasteries followed disciplined schedules. But for many people, the clock remained a guide rather than a master. The Industrial Revolution gradually changed that relationship. Beginning in the late 18th century and accelerating throughout the 19th, factories gathered hundreds of workers beneath a single roof. Unlike farms, factories depended upon machines. Unlike fields, machines could continue operating regardless of sunlight. Unlike individual craftsmen, hundreds of workers now depended upon one another. If one person arrived late, an entire production process might slow. If one machine stopped unexpectedly, many others could stand idle. Coordination became essential. For perhaps the first time in history, thousands of people were expected to begin work at exactly the same moment. The factory whistle became one of the defining sounds of industrial society. Much like church bells before it, The whistle reached across entire communities. Its meaning, however, was different. It announced the beginning of labor, the end of a break, the conclusion of the working day. Time was becoming increasingly connected to wages. Instead of being paid primarily for completing a particular task, many workers were now paid for the hours they spent at work. This was a subtle but profound transformation. An hour itself acquired economic value. Today, phrases such as working overtime, billing by the hour, or saving time sound completely ordinary. They carry assumptions that developed gradually during this period. Time had become something that could be bought, sold, scheduled, and measured with increasing precision. Not everyone welcomed the change. For people whose families had organized work according to daylight and seasonal rhythms for generations, factory schedules could feel harsh and unfamiliar. The clock no longer adapted to human needs. People adapted to the clock. Historians continue debating how quickly this transformation occurred and how uniformly it affected different industries and regions. Rural life often retained older rhythms for many decades, while rapidly industrializing cities embraced increasingly strict schedules. History is rarely uniform. Different communities changed at different speeds. Even so, the broader direction was unmistakable. The clock moved from church towers into factories, from factories into schools, from schools into offices. Eventually, it entered almost every part of everyday life. Education changed as well. Instead of beginning lessons whenever teachers and students happened to gather, schools increasingly divided the day into fixed periods. A bell announced mathematics, another announced history, another signaled lunch. Children gradually learned something previous generations had rarely experienced. Life could be divided into precisely measured blocks. Many of those children later entered factories, railways, government offices, or businesses where exactly the same system awaited them. The clock quietly shaped expectations long before adulthood. Transportation reinforced these habits. Railway timetables demanded punctual passengers. Missing a departure by 2 minutes could mean waiting hours for the next train. Steamships operated on published schedules. Postal services promised deliveries within predictable periods. Businesses expected correspondence to arrive according to organized timetables, rather than uncertain journeys. Entire economies became increasingly dependent upon reliable synchronization. Even language began changing. People spoke about running out of time, making time, losing time, investing time. Time became something that resembled money. Not because the two are identical, but because both had become valuable resources that required careful management. The transformation reached into the home. Family meals often shifted toward more regular schedules. Pocket watches became increasingly affordable during the 19th century, allowing many people to carry personal timekeepers rather than relying solely on church towers or public clocks. For the first time, time became personal. A worker no longer needed to hear the factory whistle. A glance into a pocket could provide the answer. This quiet change altered daily experience in subtle ways. Responsibility shifted. The public clock still existed. Increasingly, individuals carried their own. Punctuality gradually became associated not merely with obedience, but with professionalism, reliability, and courtesy. Being on time acquired moral as well as practical meaning. Of course, industrial society also brought criticism. Writers, philosophers, and social reformers questioned whether increasingly rigid schedules left enough room for rest, family life, creativity, or reflection. Some argued that machines had liberated humanity from exhausting labor. Others worried that people themselves were beginning to live like machines. The debate continues today. Modern technology allows many of us to work from almost anywhere. At the same time, smartphones and laptops often blur the boundary between working hours and personal life. The clock has become more flexible. It has also become more constant. Notifications arrive throughout the day. Meetings span continents. Messages cross oceans in seconds. Many people carry the office inside their pocket without even realizing it. The relationship between work and time continues evolving, yet one remarkable fact remains. None of this would have been possible without increasingly accurate clocks. Factories depended upon them. Railways depended upon them. Schools depended upon them. Modern civilization itself gradually learned to move according to their rhythm. By the beginning of the 20th century, accurate mechanical watches had become symbols of precision, responsibility, and technological achievement. It might have seemed that centuries of refinement had finally perfected personal timekeeping. Then, a tiny crystal, almost unnoticed at first, quietly began replacing centuries of mechanical craftsmanship. The next revolution would not come from better gears or finer springs. It would come from electricity itself. For nearly 700 years, mechanical clocks dominated the history of timekeeping. Generation after generation of clockmakers refined gears, springs, escapements, and pendulums with astonishing skill. Tiny improvements accumulated across centuries. Watches became smaller, clocks became more accurate. Craftsmanship reached extraordinary levels. By the beginning of the 20th century, many believed mechanical engineering had nearly reached its limits. It had not reached the end of timekeeping. It had merely reached the end of one chapter. The next revolution would emerge from a property of nature that had quietly existed all along. Hidden inside an ordinary crystal, quartz. At first glance, quartz appears completely unremarkable. It is one of the most abundant minerals on Earth. It forms inside rocks. It appears in mountains. It can even be found in ordinary sand. Few people looking at a small piece of quartz would imagine that it would eventually replace one of humanity's greatest mechanical inventions. Yet quartz possesses an extraordinary characteristic. When mechanical pressure is applied to certain quartz crystals, they generate a tiny electrical voltage. Even more remarkably, the opposite is also true. Apply an electrical signal to a carefully shaped quartz crystal, and it begins vibrating at an extremely stable frequency. This phenomenon is known as the piezoelectric effect. Discovered during the 19th century by the brothers Jacques and Pierre Curie, it would eventually transform almost every clock on Earth. The principle seems almost magical. Supply electricity, the crystal vibrates. Stop the electricity, the vibration stops. Most importantly, every vibration occurs at an astonishingly consistent rate. Nature had once again provided a rhythm, far more stable than complicated machinery alone could achieve. Instead of regulating gears with pendulums, engineers could regulate electronic circuits using vibrating crystals. The first quartz clocks appeared during the 1920s. They were enormous. Some occupied entire rooms. Far from replacing household clocks, they served primarily in laboratories and observatories, where extreme precision mattered more than size. Even in these early forms, their superiority became obvious. A good mechanical clock might lose several seconds each week. Quartz clocks reduced those errors dramatically. As electronic technology advanced through the middle decades of the 20th century, quartz devices became steadily smaller, cheaper, and more reliable. The invention of the transistor accelerated this transformation even further. Bulky electrical equipment gradually shrank into compact circuits. By the late 1960s and early 1970s, quartz wristwatches were beginning to reach ordinary consumers. What happened next reshaped an entire industry. For centuries, mastering watchmaking required years of apprenticeship. Craftsmen polished tiny gears by hand, adjusted springs, balanced escapements, assembled hundreds of delicate components with extraordinary patience. Quartz watches required a very different kind of expertise. Instead of relying primarily on mechanical precision, they relied upon electronics. Many contained far fewer moving parts than traditional mechanical watches. They proved more accurate, often more durable, usually less expensive to manufacture. consumers noticed. Within only a few decades, millions of people around the world replaced mechanical watches with quartz models. The transformation became so dramatic that historians of watchmaking often refer to this period as the quartz crisis. For many traditional manufacturers, particularly in Switzerland, the change was devastating. Companies that had dominated global watchmaking for generations suddenly struggled to compete with inexpensive, highly accurate electronic watches produced elsewhere, especially in Japan. Factories closed, jobs disappeared, entire business models collapsed. It was not because mechanical craftsmanship had become worse, it was because a different technology now solved the same problem more effectively for most customers. History has repeated this pattern many times. Steam engines gave way to internal combustion. Film cameras yielded to digital sensors. Paper maps surrendered much of their role to satellite navigation. Quartz watches joined that long history of technological change. Remarkably, mechanical watches did not disappear. They simply acquired a different meaning. Today, many people choose mechanical watches not because they are more accurate. They are not. A well-made quartz watch generally keeps better time than an ordinary mechanical one. Instead, mechanical watches became objects of craftsmanship, engineering, tradition, and artistry. Collectors admire the intricate movement of gears that remain almost entirely unnecessary from a practical standpoint. In an age of electronics, mechanical watches remind us how beautifully complex, purely mechanical engineering can be. Meanwhile, quartz quietly conquered everyday life. Look around your home. The microwave oven probably contains a quartz oscillator. The wall clock may use one. Your digital alarm almost certainly does. Computers rely on quartz crystals to coordinate billions of electronic operations every second. Televisions, radios, automobiles, medical equipment, industrial machinery, communication networks, even devices that are not designed primarily to tell time, often depend upon quartz to keep their internal operations synchronized. The crystal became one of the invisible foundations of modern electronics. Most people never notice it. They rarely need to. The technology simply works. And perhaps that is the ultimate sign of a successful invention. It becomes ordinary. Quartz also prepared humanity for something even more extraordinary. Electronic engineering developed while researchers were simultaneously pushing the limits of atomic physics. Many of the circuits first refined for quartz timing later became essential components in increasingly sophisticated atomic clocks. In that sense, quartz formed a bridge. It connected centuries of mechanical craftsmanship with the electronic age that eventually led to today's most precise timekeeping systems. Today, your smartphone almost never relies upon a single clock alone. Inside the device, quartz oscillators maintain local timing. Meanwhile, the phone also communicates with networks whose synchronization ultimately traces back to highly accurate atomic clocks distributed around the world. Several different generations of timekeeping cooperate seamlessly inside a device that fits comfortably in your hand. Few people think about that hidden partnership. They simply glance at the screen. The correct time appears. The journey from swinging pendulums to vibrating crystals happened remarkably quickly. Another transformation is already beginning. Humanity has learned to measure time with extraordinary precision here on Earth. But what happens when we leave Earth behind? What happens when human beings begin living on worlds where a day lasts a different length, where the sun follows a different path across the sky, and where even the definition of today must be reconsidered? The history of timekeeping is no longer confined to our planet. Its next chapter is already reaching toward the stars. For almost the entire history of civilization, humanity measured time without ever questioning one basic assumption. Every clock belonged to Earth. The sun rose, the sun set. The moon completed its familiar cycle. The stars returned to recognizable positions throughout the year, Every calendar, every sundial, every church bell, every mechanical watch, every pendulum, every quartz crystal, and every atomic clock ultimately served people living on one planet. Earth quietly defined what a day meant. It defined what a year meant. It defined what morning and evening meant. For thousands of years, there was no reason to imagine anything else. Then, during the 20th century, humanity did something entirely unprecedented. It left Earth. When the first satellites entered orbit, they carried far more than cameras and radios. They carried one of history's oldest inventions: clocks. At first, sending a clock into space seemed almost routine. If a watch worked perfectly on Earth, why shouldn't it continue working a few hundred miles higher? Physics had already provided the answer. Einstein had predicted that clocks moving rapidly through space and clocks experiencing weaker gravity would measure time differently. Spaceflight offered the first practical opportunity to observe those effects continuously. The results matched the predictions with remarkable precision. A clock aboard an orbiting spacecraft does not keep exactly the same time as an identical clock resting on Earth's surface. The difference is extraordinarily small, yet it is measurable. And because modern technology relies upon astonishing precision, it cannot simply be ignored. Nowhere is this more important than the global positioning system. Many people imagine GPS as a map floating somewhere above the Earth. It is actually a conversation. Dozens of satellites continuously broadcast signals containing two essential pieces of information: their position and the exact time at which each signal left the satellite. Your phone listens. By comparing how long several signals took to arrive, it calculates where you must be. The idea sounds simple. Its execution borders on miraculous. Light travels almost 186,000 miles every second. During a single millionth of a second, a radio signal moves nearly 1,000 feet. Even tiny timing errors become enormous distance errors. A mistake measured in billionths of a second can shift a calculated position by several feet. Larger timing errors quickly grow into hundreds of yards. Eventually, navigation becomes useless. This is why every GPS satellite carries multiple atomic clocks. They are among the most carefully monitored clocks ever built. Even then, they cannot simply be left alone. Engineers constantly compare satellite clocks with reference clocks on Earth, applying corrections that account for both orbital motion and differences in gravity, exactly as Einstein's theories predict. Without those relativistic corrections, GPS errors would accumulate rapidly, eventually growing by several miles each day. Most people never notice. They simply request directions. Behind that simple instruction lies one of the most successful practical demonstrations of modern physics ever performed. Space transformed clocks from scientific instruments into essential infrastructure. Yet orbiting Earth is only the beginning. Imagine taking your favorite wristwatch to the moon. It continues ticking normally. The gears still move. The electronics still function. The battery still provides power. The problem is not the watch. The problem is the meaning of time itself. A lunar day differs enormously from a day on Earth. From one sunrise to the next, the moon rotates so slowly that nearly 29.5 Earth days pass. Morning unfolds gradually. So does evening. Night lasts for roughly 2 Earth weeks. Daylight lasts for roughly 2 more. If astronauts eventually establish permanent settlements there, what should they call 9 o'clock in the morning? What exactly counts as lunchtime? When should tomorrow begin? These questions are no longer purely philosophical. Space agencies and international organizations are actively studying how future lunar missions will coordinate time. As human activity on and around the moon expands, engineers will need common reference systems that allow spacecraft, surface operations, communications, and navigation to remain synchronized. Earth time remains practical for many current missions. permanent settlements may eventually require additional conventions. Mars presents an even stranger challenge. A Martian day, known as a sol, is approximately 24 hours and 39 minutes long. At first, that difference sounds insignificant. Only 39 extra minutes. One day hardly matters. A week matters more. After several weeks, Martian clocks drift noticeably away from Earth's daily rhythm. After months, the schedules no longer resemble one another at all. Scientists operating robotic rovers on Mars have already experienced this unusual reality. During several NASA missions, engineers temporarily adjusted their own working lives to Martian sols. Each new workday began roughly 39 minutes later than the previous one. Breakfast gradually shifted toward lunchtime. Meetings drifted into the evening. Sleep schedules wandered steadily around the clock. Some researchers describe the experience as strangely disorienting. Their bodies remained on Earth. Their working day belonged to Mars. For perhaps the first time in history, people lived according to another planet's sunrise. If permanent human settlements one day appear on Mars, they will almost certainly develop daily routines based upon the Martian sol rather than the terrestrial day. Schools, hospitals, transportation, factories, families. Every ordinary activity would gradually adapt to a rhythm established by another world. History would quietly repeat itself. Ancient civilizations organized life according to local skies. Future civilizations may do exactly the same, only beneath different skies. The farther humanity travels, the more complicated time becomes. Consider Jupiter. A day there lasts less than 10 Earth hours. Venus rotates so slowly that one Venusian day lasts longer than its year. On Mercury, the relationship between rotation and orbit creates patterns unlike anything experienced on Earth. Each world tells time differently, because each world moves differently. Nature has never recognized a universal day, only local ones. This realization carries a certain irony. Thousands of years ago, neighboring villages kept different local times because the sun reached its highest point at slightly different moments. Railways eventually persuaded entire nations to adopt standard time. Now humanity is preparing to leave Earth. Local time is returning. Not because civilization has become less advanced, because civilization is expanding beyond a single planet. One day, a message may travel between Earth and Mars while both worlds continue living according to different calendars, different mornings and different evenings. Children born on Mars may think of a sol as perfectly ordinary. Earth's 24-hour day may seem just as unfamiliar to them as a Martian day seems to us. History reminds us that this would not be unusual. Every civilization assumes its own way of measuring time feels natural. Future generations may inherit rhythms we have not yet imagined. The deeper lesson reaches beyond astronomy. Humanity has spent thousands of years believing that better clocks would eventually reveal one perfect system of time. Space teaches the opposite. Precision increases, universality becomes more complicated. The universe contains countless rhythms. Each world writes its own calendar across the sky. Earth's clocks remain extraordinary. They are no longer the only clocks that matter. As humanity prepares for voyages lasting months, years, and perhaps even generations, another question quietly emerges. If we can build clocks accurate enough to navigate the solar system, how much more accurate can they become? Is there a final limit to precision, or is the history of timekeeping still only beginning? Throughout this journey, one pattern has appeared again and again. Every generation believed it had built the best clock that would ever be needed. Every generation was eventually proven wrong. The first observers trusted the rising sun. Then came shadow clocks, water clocks, mechanical clocks, pendulums, quartz crystals, atomic clocks. Each invention seemed almost perfect, Each eventually revealed its own limitations. History suggests that timekeeping has never truly reached a final destination. It simply enters a new chapter. Today, humanity stands at another turning point. The atomic clocks that quietly support GPS satellites, communication networks, financial systems, and scientific laboratories are among the most accurate instruments ever created. Yet physicists are already building something even better: optical atomic clocks. To understand why they represent such a remarkable advance, imagine two musicians keeping rhythm. One taps a drum once every second. The other plays a note that vibrates trillions of times during that same second. Which rhythm allows more precise measurement? The second one, simply because it contains vastly more individual cycles to count. The same principle applies to clocks. Traditional cesium atomic clocks use microwave radiation associated with a particular atomic transition. Optical clocks rely on atoms or ions whose transitions occur at much higher frequencies in the visible or near-visible part of the electromagnetic spectrum. Instead of counting billions of oscillations each second, they effectively count hundreds of trillions. More cycles. Greater precision. The engineering required to achieve this is astonishing. Scientists cool individual atoms until they move extraordinarily slowly. Lasers hold them almost motionless inside carefully controlled electromagnetic fields, or structures known as optical lattices. Additional lasers probe the atoms with extraordinary stability. Every source of disturbance, temperature, vibration, stray magnetic fields, even tiny environmental effects, must be minimized. Building one of these clocks is less like assembling a traditional instrument and more like creating a carefully controlled laboratory devoted entirely to measuring one tiny natural rhythm. The results have exceeded expectations. Some modern optical clocks are so stable that, under ideal conditions, they would require periods vastly longer than recorded human history to accumulate an error of approximately 1 second. As the technology continues improving, scientists increasingly discuss whether the international definition of the second should eventually move beyond cesium and adopt one of these newer standards. That decision has not yet been made. Researchers around the world continue comparing different optical clock technologies to ensure that any future redefinition would benefit science for generations to come. Remarkably, these clocks do much more than tell time. They have become scientific instruments capable of exploring the universe itself. Einstein showed that gravity changes the passage of time. Optical clocks measure those changes with extraordinary sensitivity. Raise one clock slightly higher than another, and the difference in Earth's gravitational field becomes just a little smaller. General relativity predicts that the higher clock should tick slightly faster. Modern experiments have confirmed this prediction over surprisingly small differences in height. In effect, clocks are becoming instruments that can sense gravity. This opens remarkable possibilities. Future networks of ultra-precise clocks may help scientists study subtle changes in Earth's gravitational field. Such measurements could improve our understanding of volcanic activity, the movement of groundwater, the melting of large ice sheets, or long-term changes in Earth's shape. Researchers are actively investigating these possibilities. The clock is quietly becoming a new kind of scientific sensor. Physicists are also asking even larger questions. The universe appears to contain far more than ordinary matter. Galaxies rotate too quickly to be explained by visible stars alone. Large-scale observations suggest that unseen matter influences the evolution of the cosmos. Scientists call this mysterious component dark matter. Despite decades of research, no one knows exactly what it is. Some theoretical models suggest that certain forms of dark matter might produce extraordinarily tiny changes in fundamental physical quantities. Networks of exceptionally stable atomic clocks could, in principle, help search for such effects by looking for synchronized changes that cannot be explained by ordinary physics. Whether these experiments will reveal anything remains unknown. The possibility itself illustrates how far clocks have traveled from their ancient origins. Humanity once used them to decide when to plant crops. Now they may help investigate some of the deepest mysteries in cosmology. Other researchers look toward quantum technologies. Quantum mechanics already lies at the heart of every atomic clock. Future quantum sensors may push precision even further. Exactly how far remains an open question. Every increase in accuracy demands overcoming new physical challenges. Tiny vibrations become significant. Minute temperature changes matter. Even effects that once seemed completely negligible begin influencing measurements. The closer scientists approach perfect precision, the more carefully they must understand the universe itself. History repeats. Better clocks require better physics. Better physics inspires even better clocks. The cycle continues. Perhaps the most fascinating question is whether there is an ultimate limit. Can time be measured with unlimited precision? Or does nature eventually impose a boundary beyond which no clock can ever improve? Modern physics does not yet provide a complete answer. Quantum mechanics introduces fundamental uncertainties into many measurements. General relativity describes gravity with extraordinary success. Physicists continue searching for a deeper framework capable of unifying these theories. Many suspect that understanding time more completely will play an essential role. Until then, the history of clocks remains unfinished. One day, children may learn about cesium clocks the way we now learn about pendulums. Museum visitors may admire today's technology as an important step towards something even more remarkable. Future explorers traveling beyond our solar system may carry clocks unlike anything humanity has yet imagined. History encourages humility. Every generation has believed it stood near the end of the story. Every generation eventually discovered another chapter waiting to be written. Perhaps that is the true lesson of timekeeping. Humanity never stopped asking better questions. The first observers asked when winter would end. Astronomers asked how the heavens moved. Engineers asked how to build more reliable clocks. Navigators asked how to cross oceans safely. Physicists asked whether time itself could change. Today's researchers ask whether clocks can help reveal the structure of space-time, the nature of gravity, and perhaps even the invisible components of the universe. Tomorrow's questions will almost certainly surprise us, just as Einstein would have surprised the makers of medieval tower clocks. Just as atomic clocks would have astonished Galileo, just as a mechanical watch would have seemed miraculous to the first people who measured daylight with nothing more than a shadow. The history of time has never really been about clocks. It has always been about curiosity. Every clock humanity has ever built represents the same quiet hope, that if we measure the universe carefully enough, it may reveal one more secret. And judging by everything that has happened over the past several thousand years, it almost certainly will.